Okay, so first of all, state that there are positive and negative charges and the charge is measured in coulombs, right? So first of all, I'm going to cover all the pointers that are pretty straightforward, right? So for example, we know that there are positive and negative charges and that charge is going to be measured in coulombs, right? And we also know that unlike charges are going to attract and like charges are going to repel. Okay, the syllabus pointers that focus on stating, you just need to be able to state, that's it, right? Now state examples of electrical conductors and insulators, that also we know that it's going to include, if we talk about insulators, that's going to include substances like things like glass, silk, wool. If we talk about electrical conductors, that is going to mainly revolve around metals. For example, we have copper, iron, steel, graphite, fluids, liquids, gases, that they're basically substances that are going to contain mobile charged particles, right? Moving particles, right? Ions or electrons. Okay, so first of all, unit of charge. Charge is measured in coulombs, that we already know, and the charge on an electron is 1.6 into exponent minus 19 coulomb, right? Then we have this experiment. This is the, I think, the one and only detailed part of this. And electrostatic induction is the second detailed part. So a gold leaf, okay, so this is basically, an apparatus that you can see here. A gold leaf electroscope consists of a metal cap on a metal rod. So you can see the metal rod right here, and you can see the metal cap here, right? And you can see also an insulating plug. Then you have a metal plate here. Then you have a gold leaf. This thing is a gold leaf, okay? Then you have a glass window, wooden or metal case, earth by resting on bench. Okay, so that is basically not going to have any charge. Earth means that. Okay, so a gold leaf electroscope consists of a metal cap on a metal rod at the foot of which is a metal plate with a leaf of gold foil attached. The rod is held by an insulating plastic plug in a case with glass sides to protect the leaf from draughts. Detecting a charge. Bring a charged polythene strip towards the cap. So where is the cap? You can see the cap, right? So you're going to do what? You're going to bring the charged polythene strip. Polythene, is simply, that plastic, okay? And you can simply charge it by friction, right? So if you're going to rub polythene against anything, it's going to become charged, right? So what you're doing is that you have a metal cap here, and this apparatus right here has the capability to detect charge, right? So you're bringing the charged polythene strip towards the cap. Okay, so the leaf rises away from the plate. This leaf is going to rise away from the plate, right? When you remove the charge strip, the leaf falls again. Okay, so when you're going to, so basically what's happening is that if you bring a charged polythene strip near to the cap, this leaf is going to move, apart. And then when you're going to remove it, it's going to fall again, right? So this can be used to detect charge. That is the first thing. Draw a charged polythene strip firmly across the edge of the cap. The leaf should rise and stay up when the strip is removed, right? So this is charging by contact, right? So when you're going to draw a charged polythene strip firmly across the edge of the cap, then it's gonna remain charged. So it's going to remain up, it's not gonna fall down again, right? So that is charging by contact. Then what's happening? If it does not, repeat the process but press harder. So basically, first of all, we just brought the polythene strip near to it, okay? But if you're going to firmly press it, then that is going to keep the leaf above, right? So that means that you have charged by contact. The electroscope has now become negatively charged by contact with the polythene strip from which electrons have been transferred, right? So this is what's happening, and this is how this gold leaf electroscope can be used to detect charge and to charge by contact. Then we have insulators and conductors. Test the cap of the charged electroscope with different things, such as a piece of paper, a wire, your finger, a comb. So as you can see, we have different things here, right? Some of them are insulators, some of them are conductors, right? When the leaf falls, charge is passing to or from the ground through you and the material touching the cap. If the fall is rapid, so if it's going to fall rapidly, then that means that the material is a good conductor. However, if the leaf falls slowly, then the material is a poor conductor. Why is that happening? Because when you're going to have an insulator, you know that an insulator is going to have, charged particles would not be free to move about in an insulator, right? So what's going to happen when the particles would not be free to move about? It's gonna conduct the charge for a longer time, so it's gonna fall slowly, right? So I mean, it's not gonna conduct the charge for a longer time, but the charge will stay at one place for a longer time, right? But if you're going to have a conductor, that is going to conduct charge better because it has more charged particles, right? So they're going to carry the charge. So when that's going to carry a charge, what that's going to ensure is that Because of that, your fall of the leaf is rapid, right? So basically you bring a conductor, you bring a good conductor near to it, right? So what's going to happen now, that conductor has more charged particles, right? So they're moving the charge. So because of that, it cannot charge by contact for a longer period of time. Okay, so this is what's happening. The gold leaf electroscope used in this experiment could be replaced by an electronic instrument capable of measuring electric charge. For example, if you can have an electrometer. How could you charge a polythene rod? We can simply do it by rubbing against a material. How could you transfer charge from the polythene rod to a gold leaf electroscope? By pressing harder. Why does the leaf of the electroscope rise when it gains charge? Because it's going to gain charge from it. It's going to gain negative charge. So it's going to repel the metal plate, right? How can you discharge electroscope? What can you do for that? You can simply remove the um, whatever material you brought near to the metal cap. Okay, right? So that is what's happening here. Then we have, okay, now they're probably going to provide you an explanation here. In an insulator, all electrons are bound firmly to their atoms, right? So this is what I was discussing. In a conductor, some electrons can move freely from atom to atom. An insulator can be charged by rubbing because the charge produced cannot move from where the rubbing occurs, right? That is, the electric charge is static because we have less charged particles to carry the charge. A conductor will become charged only if it is held with an insulating handle. Otherwise, electrons are transferred between the conductor and the ground with a person's body. Good insulators include Good insulators include plastics such as polythene, cellulose, acetate, perspex, and nylon. All metals and carbon are good conductors. In between are materials that are both poor conductors and, because they conduct to some extent, poor insulators. Examples are wood, paper, cotton, the human body, and the earth. Okay. Then we have water conducts, and if it were not present in materials such as wood and on the
स्टैटिक का
surface,
क्या मतलब है?
remains at one place. Static charge यानी एक जगह पे रहेगा, ठीक है? So these will be good insulators. Dry air insulates well. Okay, so this was all for our electrons, insulators, and conductors. Okay, so I want to, I think, yes, I want to do it separately now. Right. Okay, so now if we are going to compare, we can now compare like electrical insulators and electrical conductors, right? So for example, if I talk about this, first of all, I'm going to talk about the motion of charged particles, right? So if I'm going to compare them, what can I write? I can write that basically we have charged particles are not free to move about. Particles not free to move about. Okay, and then here we know that charged particles are free to move, right? So we can write that down. Charged particles free to move. Okay, then here we can go for another thing is that ability to conduct electricity. Conduct electricity. Then that also we know that here it will be low and here it will be high, right? Then we can also have method of charging that we're going to study right now. Okay, method of charging. So here it's going to be by friction. That is basically that when electrical conduct insulators become charged, the electrons remain at the surface, where the material has been rubbed. Spin, rub. Okay, and here what's going to happen, here you can charge by induction, that we're going to study right now. Okay, and examples, last column. Examples here can be glass, perspex, we have silk, wool, Okay, here we can have copper, iron, metals, basically anything that contains mobile electrons. Okay, mobile particles actually. Okay, so this is the summary. Okay, now I'm going to discuss two things here, right? So first of all, what I want to discuss is um electrostatic charging by friction, because that is how our insulators are charged, right? So let's discuss that first. Electrostatic charging by friction. Okay, now let's talk about this. So basically, first of all, let's talk about what is electrostatics, right? Electrostatics is going to be the study of static electric charges, right? For example, if you talk about some materials such as glass and silk, these things are going to get electric charges when they're going to be rubbed together. Okay, why are they going to get charges when they're going to be rubbed together? This is because rubbing is going to transfer electrons from one material to another, right? And we know that electrons are negative charges, right? So what I'm telling you right now is that if you're going to rub two substances, two insulators, because insulators are the ones which are charged by friction, so that is going to result in the transfer of negative charges, right? So that's what's happening. The electrons transferred are basically unable to move about freely within the material because it's an insulator, and they remain at the surface where the material has been rubbed, right? So materials in which electrons are not free to move about are going to be called what? Electrical insulators, right? So electrical insulators are not going to conduct electricity and they are charged by friction, right? So for example, if I give you an example, if I draw, for example, if I have a metal rod sort of thing, I am trying to draw it. Okay, and I have, like, basically I have all the positive charges here. Just consider these positive symbols, right? And I have the negative charges here. Okay, so these are my negative charges, right? And then I have another thing. For example, this is, consider this a glass rod and consider this silk, right? So this is going to have positive, negative charges all over, right? So what's going to happen is, okay, so basically if you consider, so this is before I have rubbed or before I have done anything, right? So before rubbing the glass rod, and this is the glass rod, and this is the piece of silk, right? I cannot draw it better, but try to get the idea. These dots are positive symbols. Okay, so now you can see that both of them have both charges, right? Both positive and negative, right? But the thing is that I have not rubbed them or anything, so they both are electrically neutral. Okay, and what that means is that they're going to have equal numbers of positive and negative charges, right? For example, here you can see there are 4 positive charges and 4 negative charges, 2 positive charges and 2 negative charges, right? So what are they? Before charging, they are what? They are electrically neutral, right? So that is the first thing. Wait. Yes. So the first thing that we know is that before charging, what are they? Electrically neutral. Okay. Now, the second thing is what's going to happen when we're going to rub them, right? Now, different materials are going to have different affinities for electrons, right? And what does that mean, that different materials are going to have different affinities? That means that they're going to attract the electrons. Some can attract strongly, some can attract weakly, right? So basically what's going to happen is that when we're going to rub the glass rod and silk together, the atoms at their surfaces will get disturbed, right? So what's that going to do is that some electrons from the atoms or the surface of the glass rod will be transferred to the piece of silk, right? So that is going to happen, right? So as the glass rod, so basically what I'm trying to say is that different materials are going to have different electron affinities, right? Some of them will be able to lose electrons, some of them will be able to gain it, right? So what's going to happen is that in this case, our glass rod is going to lose electrons, right? And that is going to become, it is going to become positively charged, right? And the piece of silk is going to gain electrons, right? So it's going to become negatively charged, right? So basically this was the first thing, that before charging materials are not materials, actually insulators are are electrically neutral. That was the first thing that we discussed. Second thing is that different materials have different electron affinities. Okay, and because of that, someone is going to lose electrons. Okay, so if one is going to lose electrons, then what is more? Protons are more. Positive charge is more. So it's going to become what? It's going to become positively charged, right? One is going to lose electrons and become positively charged. The other is going to gain electrons and become negatively charged. Okay, so this is what the idea of electrostatic charging by friction is. Okay, so but we need to know one thing, right? Electric charges are not created or destroyed during electrostatic charging, right? They're basically simply being transferred. One of the materials is gaining it and the other is basically losing it, right? So that's what's happening. Now moving on to the second thing. Now, and that is going to be how our conductors do it, right? So let's talk about that. Now that is going to be charging conductors by induction. Conductors induction. This is the second thing. Okay, now let's talk about it. What's going to happen here. Okay, so basically now in this example we can consider two spheres, right? Two metal spheres. So first of all, what we're going to do is that we're going to place the two conductors on insulating stands, right? So how is that going to seem like? So for example, I have two spheres, right? These are two spheres and I've basically placed it on an insulating stand. Okay, so this is the first thing that which I have, right? Now in the second step, what I'm going to do is that I'm going to bring a negatively charged rod near one of the spheres, right? This one is negatively charged, right? So what is that going to do? That is going to cause the electrons in both the metal spheres to be repelled by the far end of sphere. Okay, so what I'm trying to say is, see, basically we have both of them are conductors, right? Both of them are going to have positive and negative charges, right? So what's going to happen is that if I'm bringing negative charge closer to this one, what's going to come here? We know that unlike charges are going to attract, right? So what's going to come here? Positive charges. Okay, the number is going to be same as this, right? So three of them here. Okay, now if we have positive charges here, what do we have on this side? We have negative charges, right? So three negative charges on this side. Okay, and now if there are negative charges here, then what will be here? There will be positive charges here. And if we have positive charges here, what will be here? Negative charges, right? So that is what's happening. Right now, what I'm going to do is, in the third step, what I'm going to do is that while holding the charge rod in place, this was my charge rod, by holding this in place, I'm gonna move this far away from this sphere, right? So, and then when I've done that, what I'm gonna do is that I'm gonna remove the charge rod, and now both of them are going to have equal number of opposite charges, right? So what's going to happen now is that, for example, what happened in B? What was coming near it? Positive charges, right? So now what I did was that basically I knew that I brought this near to it, right? So what happened was that positive charges came near to it, right? I had the rod near the sphere. What I did was I removed the other opposite sphere, right? So when I removed that sphere away from it, what happened was that now this sphere is going to be positively charged. And because this one had negative charges on its end, this one is going to get negatively charged, right? So this is what's happening. And this is the first thing when you're going to charge two metal spheres by induction, right? Now the second thing is, these were two spheres, right? And you charged both of them. What if I talk about charging a single metal conductor by induction, right? So again, now if I'm talking about, for example, let's take any, object, you know, and this is again my rod, okay? So what I'm gonna do is that this is my rod, and this time I have it positively charged. Okay, so this time I have it positively charged, right? And now what's going to happen is, okay, now this is positively charged here, right? Now what's going to happen is, now again the same thing is going to happen. This thing is a conductor right here, so it's going to have both of the charges, right? But if this thing has both of the charges, but I have brought what near to it, a positively charged glass rod. So what that is going to do is that it's going to attract negative charges here. And now if I have negative charges here, what do I have here? I have positive charges on this side, right? So now what's going to happen? Without removing, first thing that I did was that I brought the positively charged glass rod near the metal conductor, which is on an insulating stand. Right? Second thing that I did was that without removing the glass rod, I'm gonna earth the positively charged end and of the metal conductor by touching it with our hand. So I'm going to touch this thing, right? And what that is going to do is that is going to neutralize the positive charges on the that end of the conductor, right? So what I'm going to do is that I'm going to touch my hand, my finger on this side, on the opposite side, right? So when I'm going to do that, what that's going to do is that's going to neutralize the positive charges. Why? Now why that's happening? Because we are also made of charges, right? So when I know that the glass rod is already positively charged, right? So when I have a positively charged glass rod, that brought negative charges to that particular end, right? And on the opposite end, I had positive charges, right? What I did was that I myself am made of charges, right? So I touched my finger, I touched the positive end with my finger, and because of that, the charges got neutralized, right? Now, what I'm gonna do is, and this thing is basically called earthing, right? Now, what I'm gonna do is that with the glass rod still in place, I'm gonna remove my hand from the conductor. So I'm gonna remove my hand from the conductor, and because of this, now the process of earthing is going to stop, right? Then what I'm gonna do is that I'm gonna basically remove the glass rod, right? So I'm gonna remove this glass rod now, and what that's gonna do is that that's gonna allow this this conductor to be negatively charged, right? So the conductor will now be negatively charged, right? So if I'm to provide a summary, what I did was that I am talking about charging a single metal conductor by induction. What I did was that I had a conductor in place, and I brought a positively charged glass rod near to it, right? And because of the influence of that positive charge, what came to that end? Negative charges came to that end, and positive charges were on the opposite end. Then what I did was that I touched the positive end with my finger, so that basically neutralized that positive end, right? And because of that, what happened was that now I still have the glass rod in place. I didn't remove that, right? Now what I'm gonna do is that when I'm touching the positive end, I'm gonna remove the glass rod slowly, right? And when I'm going to do that, that is going to help, that is going to make my conductor negatively charged, right? So this is what's happening, and this is all about charging a single metal conductor by induction, right? So I'll see if I can look for some images for this, because my drawing isn't good and this isn't giving a good idea. Charging by induction, let me see. Wait, I'm looking. Right? Okay, wait, I'm searching for it. Okay, here we have it. Wait, I'll share my screen. Where is my screen? See, can you see it? See, for example, see, this is what I did before. I charged two metal spares. This is what happened, right? And I think I can get more images here. See, two metal spheres are mounted on insulating stands. The presence of a positive charge induces electrons to move from spheres B to A. The two sphere system are polarized, right? So this is what's happening here, right? Then what's happening is sphere B is separated from sphere A using the insulating stand. The two spheres have opposite charges. The excess charge distribution itself uniformly over the surface of the sphere, right? So this is what's happening. See, this is what I did by here also. Copy this image, right? So this was the summary of what we did right now, right? Let me see if I can. Right, so this is what we did. Okay, now this was all about how we can charge it, right? But we can also do another thing. We can also neutralize them, right? And a charged object can be neutralized by discharging the excess charges of it, right? So if we want to, okay, wait, give me a minute. So I think it's fine. Yes. So basically, right now, we talked about charging them, right? But we can also discharge them. And by discharging, I mean that I can remove the excess charges on it, right? So basically, when I'm talking about an object that is charged, that means if it's going to be positively charged, that means that it has excess of positive charge. If it is negatively charged, that means that it has excess of negative charges, right? So what I can do is that I can remove those excess charges, and that process is going to be called discharging, right? Now, how are we going to discharge a charged insulator, right? So what I'm going to do now is that, for example, I have a positively charged glass rod, right? So what I'm going to do is that I'm going to bring it near a flame, right? And when I'm going to bring it near a flame, the intense heat from the flame is going to ionize nearby air particles, right? So these ions are now going to neutralize the excess charges on the glass rod, and the glass rod is going to get discharged, right? So what I'm saying is that first thing I did was that I had a positively charged glass rod. I brought it near a flame, right? Then what happened was that because of intense heat from the flame, the nearby air particles are going to become ionized, right? So basically, when they're going to become ionized, I'm going to have them in the form of positive and negative charges, right? And when I'm going to have them in the form of positive and negative charges, for example, now if I have my positively charged glass rod, right? So the negative charges from the atmosphere now can neutralize those positive charges. For each positive charge, I'm going to have negative charges. So the negative charges from the atmosphere are going to move towards the positively charged glass rod, and they're going to neutralize it, right? Now, the second thing which I can do is that, for example, if I have a negatively charged balloon and that is floating in air, right? So now what I'm going to do is that we know that the water molecules in the air, they are also electrical conductors, right? So what I can do is that excess charges can be transferred to the water molecules from the surface of the balloon, right? So basically we know that the air, if the air is humid, it also has water molecules, right? And those water molecules are also electrical conductors. So if I have a negative balloon, I'm giving you the example of a negative balloon, but if I have any negative thing that is in the air, right? So what can happen that those excess negative charges can be transferred to the water molecules, right? And when those negative charges can be transferred from the water molecules, that can help discharge that particular negative thing, right? Now the proper term of discharging a conductor, this was for insulator, right? But the proper term for discharging a conductor is earthing, right? Why? Because we know that electrons are free to move about in conductors, right? So basically, when we're going to earth a charged conductor, that is going to provide a path for excess electrons to flow away from the charged conductor, and it is also going to allow the electrons to flow to the charged conductor, right? So I'll try to share an image which can explain you better. Wait. Earthing a charged conductor. Let's see. Yes, now I'm gonna share my screen, wait. But I don't need to share my screen, wait. See, now we're gonna discuss this, right? So first of all, what I'm gonna do is, okay, and now we can see that this metal sphere is negatively charged, right? Now what I can do is that earthing a negatively charged metal sphere is going to cause the excess electrons to flow away from the sphere to the ground, right? So what I'm doing is that basically I have a negatively charged sphere and this is on an insulating stand and I'm touching it, right? And the electrons are going to get transferred to the earth. And now how is that happening? Because we know that basically electrons are going to flow through our body, because we know that we are also conductors, right? And the human body is a relatively good conductor and it's going to allow the electrons to flow from the conductor to the ground, right? So what I'm going to do is that if I have a negatively charged metal sphere, I'm simply touching the metal sphere so that electrons can flow through our body to the earth, right? So because the electrons are now going to flow, because why are we talking about electrons here? Because this body is negatively charged. So when I'm going to touch it, the electrons are going to flow through our hand, through our body, to the earth, right? And that is how it can help discharge it. Now, if I'm talking about a positively charged sphere, what that's going to do is that we can, again, if it's positively charged, that means that it has more protons than electrons. So what does it need to get neutralized? It needs positive charges. So if we have, now the flow of electrons is not going to be from the sphere to the earth. Now it's going to be from the earth to the sphere, right? And what is going to move this time? This time what's going to move is that the electrons are going to move from to the sphere from the ground, because this one has lack of electrons. So the electrons are going to move from the earth to the sphere. So basically what our hand is doing is that our hand is acting as a path for electrons to move. In this case, the electrons are going to move from the negatively charged sphere to the ground. And in this case, they're going to move from the ground to the sphere, right? So this is what's happening. And this was one lengthy part which we completed right now, right? Now let's move on. Okay, so we discussed all this. Okay, now you need to remember this. This is how the electric fields or different things seem. This is going to be between parallel plates. This is going to be for a positive charge. If it's outwards for a positive charge, and it's going to be inwards for a negative charge. So remember that. ये बहुत दफा you need to draw it, right? So, and also one thing, direction of an electric field at a point is going to be the direction of the force on a positive charge. So for example, if I ask you what is the direction of electric field at this point, you can see that this plate is positively charged and this plate is negatively charged. And if I have a positive charge here, if I'm going to place, if I, okay, so what I told you was that if we'll be talking about the direction of an electric field, for example, if I want to know the direction of this electric field, I'm going to look for the force on the positive charge. So if I place a positive charge here, what's going to happen? It's going to move towards the negative charge, because opposite charges attract, right? So because it's moving downwards, what is the direction of electric field? Downwards, right? So this is how you're going to look for the direction of electric field. Then we have this part, dangers of static electricity. I don't think this is part of the syllabus. Let's see. Okay, no, this is not a part of syllabus. So let's leave it for now, right? Because I want to complete this part. I want to go fast. Okay, now. Positive and negative charges. When a strip of polythene is rubbed with a cloth, it becomes charged. That we already read right now, right? Because that is going to result in the transfer of electrons, right? So if it is hung up and another rubbed polythene strip is brought near, repulsion occurs, right? Attraction occurs when the rubbed strip of cellulose acetate is brought near. So they're simply talking about charging by friction here. So we already have the idea now. So I don't think there is a need to discuss that anymore. Now I need to go fast, right? Now, first of all, let's look through this. If we talk about electrical current, what is that? Electric current is basically charge passing a point per unit time. We know that, right? So what is going to be electric charge? Charge is going to be current into time. Charge, unit of charge is coulombs, right? Current is charge per unit time. That you can see through this formula. Describe electrical conduction in metals in terms of the movement of free electrons. We know that any material that is going to have free electrons will be able to conduct electricity. So if, how does a metal conduct electricity? Through electrons, because electrons are able to transfer the electricity through it, right? So that's what's happening. know that current is measured in amperes. We know that the SI unit of current is amperes, and that ampere is going to be given coulomb by coulomb per second. If we have 1 ampere, that can only result in by 1 coulomb divided by 1 second, right? So what is that going to be? Coulomb per second. So that means that coulomb per second is same as what? It's same as amperes, right? So know the difference between direct current and alternating current. So what you need to know about this pointer at this stage is that direct current has one direction, right? And alternating current is going to change its direction, right? We're going to do this in detail. Then okay, now let's move on to this. So as you can see, what you can see here is current is measured using an ammeter. Ammeter should always be connected in series. This is how it's going to be connected in series, right? And we know another thing is that, yes, this thing, conventional current. See, now there are two things. We have a battery, right? And a battery is going to have a positive terminal and a negative terminal, right? The current that is going to flow from the positive terminal to the negative terminal is called conventional current, and but the electrons are going to flow from the negative terminal to the positive terminal. So that is going to be electron flow, right? Now this is all you need to know about current at this stage. Now the second thing is electromotive force. If we talk about electromotive force, electromotive force is always going to be of a source, the electrical energy source. For example, if this is the electrical energy source, the EMF is going to be of this, right? And the formula for EMF is work done per unit charge, right? So work done, that is the amount of non-electrical energy converted to electrical energy, right? This thing. Now, one thing also we need to know is that how can we calculate the resultant EMF? Right now, if you look at this, see, you can see a diagram here, right? And you can see that here we have two batteries connected in series, but here we have two batteries connected in parallel, right? So what we can do is that, for example, now if I'm saying that each battery has an EMF of 1.5 volt, right? So what is going to be the resultant EMF here? We have two batteries, right? So the resultant EMF in this case is going to be the sum of EMFs, while in this case it's going to be for one battery, right? So what I'm saying is this point. When cells are arranged in series, the resultant EMF is sum of all EMFs. So for example, I have 1.5 volt, 1.5 volt. So 1.5 plus 1.5 gives me 3 volt, right? And in this case, for parallel, it's going to be that of one cell. So for one cell, it was 1.5 volt. So the resultant EMF is also going to be 1.5, right? So this is what I'm talking about here. So definitely, if I'm talking about a cell as in which a circuit in which basically the resultant EMF is the sum, so definitely these cells are going to last comparatively lesser compared to that in parallel, because for parallel they're providing just a portion of energy, right? So because of that they will last longer, right? Then moving on, we have the idea of potential difference. The unit of both EMF and potential difference is indeed volt. Okay, is volt. So as charge flows around a circuit, energy is transferred to or from the charge. The potential difference voltage between 2 points in a circuit is related to the amount of energy transferred between those points, right? So between those points are, here for the bulb it's 5 volt, here for this resistor it's 7 volt. So for EMF we talk about the source, but for potential difference we talk about a component, right? Measuring potential difference, if I want to measure the potential difference across this resistor, what I'm going to do is that I'm going to connect my voltmeter. Now this time my device is voltmeter. I'm going to connect it with parallel, in a parallel combination with the component for which I want to measure the potential difference, right? Now the last thing is resistance. Recall and use. Okay, so we know that we can measure the potential difference using a voltmeter. We know we can measure the current using our ammeter. How can we measure resistance? Now for resistance, we have a particular formula, and that formula is V upon I, which means basically that it's basically what is, see, if I talk about what is resistance. Wait, I'm gonna complete this here. See, if I'm talking about what is resistance, so the resistance of a component is going to be going to be the ratio of the potential difference V across it to the current I flowing through it. Right, so this is my definition of resistance, right? And second thing I discussed was that the formula is R equal to V upon I, right? So it's basically a ratio of V to I, right? And its unit is ohms, right? Then we have the idea, okay, now if we talk about, then we have the idea of resistors, right? Resistors. So basically, if I talk about what is a resistor is going to be conductor in a circuit that can be used to control the size of the current flowing in a circuit. How can it be used to control the size of current flowing in a circuit? Basically, you know that if I can control the current, this is the current, right? So definitely a resistor is going to have a particular resistance. If that resistance can be varied, then what can be controlled? Current. Why? Because resistance and current are related through this formula, right? So this is what the second pointer is about. For example, so a resistor is a conductor in a circuit that can be used to control the size of current flowing in a circuit, right? Okay, this is the first thing that we need to know. Next thing that we need to know is that there are two types of resistors. Right? One is going to be my fixed resistor. Right? Now, if I'm talking about a fixed resistor, its resistance is going to have a fixed value, and the other is going to be a variable resistor. Okay, so these are the two things that I need to know about resistors, right? Then we have the idea of how can we measure resistance. Okay, so first thing I told you was that if I need to calculate the resistance, I need to know the current and the voltage, right? The EMF, right? So what can I do? The potential difference, right? In this case, because we're talking about a particular component. Okay, so for example, now if I talk about a particular circuit component for which I need to measure the resistance, right? Now what I'm gonna do is that for that I'm gonna use a rheostat. What is rheostat? Rheostat is basically a variable resistor, right? So what I'm gonna do is that first of all, I need, you know that if I need to calculate the resistance, I'm gonna need the ammeter reading and I'm gonna need the voltmeter reading, right? So what I'm gonna do is that first of all, I'm gonna adjust the rheostat such that it allows a larger current to flow in the circuit, right? So first of all, what I did was that I'm gonna keep the initial current in the circuit small, right? So I'm gonna adjust the rheostat to its maximum value. So when resistance is going to be maximum, what is going to be lower? The initial current is going to be small, right? Then what I'm gonna do is that I'm gonna allow a larger current to flow through it. And if I want a larger current to flow through it, what I'm gonna do is that I'm gonna decrease the resistance of the rheostat, right? So when I have the values, I'm gonna basically, what I can do is that I can record various values at this point, right? So what I'm going to do is I have a rheostat, I have a variable resistor which is in my circuit, and what I'm doing is that for that I can draw it actually. Wait.
ये टाइप्स एक्सप्लेन करना दोबारा.
Acha, wait, I'm explaining. See, basically what I'm saying is I need to measure what? I need to measure resistance, right? Okay, wait, how is, right? See, if this is my bed. God, this is not at all good drawing, but this is considered my battery, right? Now what I have is that I know that I'm gonna have my ammeter in place, right? This is my ammeter. This is the particular circuit component I want to measure, right? Then I have a rheostat connected in series, of course, right? And I have, I can complete my circuit like this, and I need to measure, and you know that the rheostat is like this, right? It has an arrow across it, right? And I also know that I need to measure the resistance for this, right? So what I have is a voltmeter connected in parallel, right? So this is a rough example of how my circuit is going to look, right? Now what I'm going to do is, see, when you talk about this formula, what can you see? You can see basically, if I want to know the relationship between resistance and current, what I can do is that I can bring current and resistance on one side, right? So if I'm going to shift current to that side, current and resistance are going to multiply. If two things multiply at one side, that means that the relationship is inverse, right? If I'm going to bring V and R on one side, they're going to divide. That means that their relationship is direct. What that means is that if the relationship is inverse, if I'm going to increase one thing, the other thing is going to decrease. So if I'm going to increase resistance, my current is going to decrease, right? And for voltage, if I'm going to increase the resistance, my voltage is also going to increase, right? So this is how we can judge the relationships. So what I can do is that I have my rheostat. If I'm going to increase the resistance to its maximum, then current is going to be at its lowest, right? If I'm going to decrease the resistance, then the current is going to be at its maximum, right? So what I'm saying is that I can adjust the current, I can adjust the resistance to have different values of current, right? So what this I'm gonna do this, I'm gonna record some values based on this thing. When I'm gonna have at least 5 sets of values, I'm gonna draw a graph, right? Now you know that gradient is equal to change in y upon change in x. Now if I draw a graph and I keep voltage on my y-axis and I keep current on my x-axis, then my gradient is going to be v upon I, right? So if I have v upon I, what is v upon I? V upon I is indeed resistance, right? So if I calculate the gradient of the graph, what I'm going to get? I'm going to get resistance, right? So this is how I can measure resistance. Now another thing that we need to know is, so this was this thing, right? How can we calculate resistance using a voltmeter and ammeter, and we can do the appropriate calculations, okay? And I just told you the direct proportionality thing also, and now we need to discuss this point. Direct proportionality between resistance and length, inverse proportionality between resistance and length. Okay, now we need to all of this, right? So basically now we're moving on to something we call the Ohm's law. Wait, let's discuss that. Ohm's law. Okay, so if I talk about what the Ohm's law is, the Ohm's law is, wait, it states that the current passing through a metallic conductor is directly proportional to the potential difference across it, provided that physical conditions conditions not conditions actually, conditions such as temperature, remain constant. Okay, so see, I just told you that if you want to judge the relationship between two things, you bring them on one side, right? So if they're saying that potential difference is directly proportional to current, current is directly proportional to potential difference, I can also write it like V upon I, because I know that if two things are supposed to be directly proportional, they're supposed to divide when brought near on the one side, right? So if I talk about V upon I, what is V upon I? V upon I is R, right? So if V upon I is R, what is supposed to be constant? R is supposed to be constant, right? So this is what I mean by this. I'm gonna look for the graph as well, and I'm gonna attach it here as well. Wait. Um, graph of ohmic conductor. Wait. So basically, it's a straight line. Wait, I'll put it here. See, it's going to be like this, right? This is how the graph for a ohmic conductor is going to look like. Okay, so if I talk about a non-ohmic conductor, so for what about that, right? So if I'm talking, okay, so for non-ohmic conductors, we need to know about two things, right? First of all, we need to know, okay, non-ohmic conductors, non-ohmic conductors. I need to know about two things. I need to know about my filament lamp, right? And I need to know about semiconductor diode. Okay, so if I talk about a filament lamp, what is the function of a filament lamp? The function of a filament lamp is to convert electrical energy to light and heat energy. Right, this is my function of filament lamp. Right, now I need to be able to provide a description of the graph. First of all, let me show you the graph. Wait, PI graph filament lamp. So see, my graph is going to be like this. See, my graph is going to be something like this. Now, why is the graph like this? Because of this. Okay, as the current is going to increase, or this just right increases, the device generates more heat. So what if it's going to generate more heat, what's going to happen? Thus, the temperature is going to increase. Is going to increase. First thing. Now, as temperature is going to increase, what's going to increase? Increases. Resistance increases. We just said that if one thing, if something needs to follow, if a metallic conductor needs to follow Ohm's law, the physical conditions should remain same. Why? Because if you're going to change, if you're going to increase the temperature, what's going to change? The resistance is also going to increase, right? So what's going to happen in this case is that the resistance of the filament is going to increase. Right, this is the second thing that you will know about. Okay, so what you can see here is that the IV graph of the filament lamp is showing you that the resistance is also increasing with temperature, right? So this was for this. Second thing we need to know about is a semiconductor diode. Semiconductor diode. Okay. So if I talk about a semiconductor diode, what is a semiconductor diode? It's a device that allows current to flow in one direction. One direction, right? Which is the forward direction, right? So I'll show you the graph again. Right? Diode. So my graph is going to be like this. Okay, so what you can see here is, now I'm going to tell you what the graph means, right? So the graph, you can see what that when my potential difference is applied in forward direction. Why? Because you can see voltage is increasing, right? So when potential difference is applied in forward direction, forward direction, what is going to increase? The current flow is large because it allows current to flow in one direction. So it allows current to flow in forward direction basically. So the current flow is going to be relatively large in the forward direction, right? So the current flow is large, right? So if the current is large, what is low? Resistance is low. So if we talk about potential difference in the reverse direction, then there is almost no current flow. And this is because the resistance is going to be really high, right? So this was all for today. I'm going to continue tomorrow. Okay.